Hi, my name is Ali Hernandez, and the topic of my presentation is how to extend the economic life of the gas lift method in a field where the reservoir pressure is constantly decreasing. First, I'm going to give a brief introduction to explain what the problem is. Then I'm going to explain what I mean by first stage optimization, where no workover is required, followed by a presentation of several alternative completions that can be used to increase the efficiency of the gas lift method. I'm going to say a few things about automation, control, and data acquisition. We might feel that because the wells are not producing as much as they used to, we shouldn't spend any money on automation, but it's actually quite the opposite. I'm going to also talk about surface facility because this is all about adapting to a new reality. And then I'm going to wrap up the presentation with some conclusions. As the reservoir pressure declines, the liquid production of the well, represented here by this blue line or curve, will also decline. This will be the well producing in natural flow, and then we introduce gas lift. So we increase the liquid production, but it continues to decline as the reservoir pressure declines. On the other hand, the injection gas liquid ratio, represented here by this red curve, will increase as the reservoir pressure declines until a point is reached at which we are no longer capable of producing the well in an economic fashion. We can, before this point is reached, we can go from continuous to intermittent gas lift to lower the injection gas liquid ratio and increase the liquid production. Or we can go either from continuous or intermittent gas lift to use other type of completion in continuous or intermittent gas lift to further increase the efficiency of the gas lift method. The first thing that we need to do is to check if the current injection gas liquid ratio is really the best that we can have. And we'll do that by selecting a representative number of wells in the field and doing a complete troubleshoot analysis in those wells to understand why some of them are not producing in a stable manner. Also find out where the point of injection is, if it is the point of injection that maximizes liquid production. Check if we have completion integrity issues or formation damage, sand accumulation, and so on. So one of the things that I recommend here is to go for CO2 tracing, because with CO2 tracing, you know, in the field, as long as the injection gas flow rate and pressure are constant, you should be able to find out where the point of injection is, and or if you have multi-pointing. Now this CO2 tracing now is being improved, and now we can continuously measure the entire composition of the injection and production gas. So we no longer have to inject CO2, we can inject CO2 or nitrogen or whatever. And that will give you also the point of injection depth, and even you can calculate even the injection gas flow rate. Now, at this stage, you have to make sure that the measurement of the injection gas liquid rate is correct. This is usually not the case in the field, so you have to make sure that that is correctly measured. The other thing that is not measured correctly is the water cut and also the gas oil ratio. Of course, the gas oil ratio depends on how accurate the total gas production is being measured, and the water cut and the injection rate. So you have to make sure that you're doing that with reliable data. Once you know that all these selected wells are doing okay, then it is time to find what we call the gas lift performance curve. If we plot the liquid rate versus the injection gas liquid ratio, we should be able to get this curve. But we get this curve not by using PySim or Prosper or Wellflow or whatever software you're using. We have to go to the field and perform on each of these selected wells multi-rate tests. We just test the well at different injection gas flow rate, so that we can maybe with 3 or 4 tests we can come up with the performance curve. Keeping in mind that we should never go below the minimum injection gas flow rate where we run into instability problems, and also if we go too far and we inject too much, we also get instability problem because of we might be opening and closing and unloading valve. Once we have the performance curve measured in this way, then it is time to extrapolate the results to the field and make sure that all well models are calibrated. Once you've done that, then you should be able to find this optimum point of injection by applying programs like GAP or PySimNet to correctly perform gas allocation. And at that point, then you should be able to realize if the current injection gas liquid ratio is really efficient, or there is room for further improvement of the gas lift method. If we are going to shift from continuous to intermittent gas lift, we need to understand that this is the aim is to reduce the injection gas liquid ratio and not necessarily to increase the liquid production by spectacular increases. We should be able to obtain from 20 to 30% increase in liquid production if we do everything right. Now, when do we go from continuous to intermittent lift? That's a question that has no theoretical answer. Many people have tried to come with dimensionless number, but there is not really one that we can say that works. But there are rules of thumb, like for example, the distance between from the bottom, the top of the perforation to the static liquid level, if it is less than or equal to 1/3 of the TBD depth of the top of the perforation, or if the reservoir pressure is less than or equal to 150 psi times the TBD of the perforation measured in thousands of feet, then it might be time to go from continuous to intermittent. Where should we apply intermittent lift? Well, we need to avoid extreme cases. For example, if the tubing diameter is too big, then we might have problems, because what I have found in many places is it's not so much that we need more gas per cycle, but because at the same time we will produce more liquid per cycle, because the volumetric capacity, the liquid volumetric capacity is large. So the injection gas liquid ratio will be more or less the same. That's not the problem. The problem is that the system might not be able to provide the gas flow rate that is needed across the valve, the operating valve, in order to sustain a liquid slug velocity of around 1,000 feet per minute. That velocity has to be maintained, because that's how we minimize the fallback losses. Fallback losses is that portion of the initial liquid slug that is not produced to the surface because it's left behind. And we're talking about usually from 5 to 6% of the initial slug velocity, of the initial slug, per each 1,000 feet of depth of the point of injection. So, for example, if we have 5% liquid slug velocity in a well that is 10,000 feet deep, where the operating valve is at 10,000 feet deep, then we're going to lose 50% of the initial liquid slug that will never be produced because of fallback losses. So the problem with very large tubing diameter is that we're going to need also a very high injection gas flow rate, instantaneous injection gas flow rate through the valve. We might be able to inject all the volume that we need, but the problem is how can we inject that volume precisely the period of time that is needed for the liquid slug to reach that velocity. On the other hand, if the tubing diameter is very small, then we're going to need to cycle the well at a very high frequency. So we end up injecting the time that is needed to inject the gas in proportion is going to be greater, and we're going to lose total daily production. Now, the same goes for the annulus. If we have a very large volume, in the annulus, then in order to pass the volume, the total volume of gas per cycle that we need to pass, we might need a very small spread. The spread of a valve is the difference between the opening and closing pressure of the valve. So because the volume is so big, that spread needs to be very small. Now, the spread of the valve is proportional to the area ratio. Is proportional to its area ratio. So when we do the calculation, the theoretical area ratio that we need once we finish the calculation might be lower than the one that is commercially available. Okay, so, and that's very bad because we're going to end up over-injecting the well per cycle, which is precisely what we don't want. Now, one of the things that we can do here is to lower the calibration pressure of the valve, the opening calibration pressure of the valve, because the spread of the valve is also proportional to its opening pressure. But here, if we are going to lower the pressure, then we have to make sure that at that new lower opening pressure, the delta P across the valve is going to be large enough in order for the liquid slug velocity to be high. Now, on the other hand, if the volume, the annulus volume is very small, maybe because the well is very shallow or because the inside diameter of the casing is very small, then we might end up calculating an area ratio that is higher, area ratio of the gas lift valve, that is higher than the one that is commercially available. But here, the situation is a little bit different because there are ways to fix the problem. One way is to increase the calibration pressure of the valve, of the operating gas lift valve, because as I said, the spread of the valve is also proportional to its calibration pressure, but you might be already at a very high injection pressure, and you might begin to open an unloading valve. So what you can do in that case is to introduce the use of a surface intermitter. With a surface intermitter, there's a valve that is either 100% closed or 100% open. The gas flow rate that passes through that intermitter at the surface is much greater than the gas flow rate that passes through the gas lift valve downhole. That means that you can force the valve to remain open for as long as you need by keeping the intermitter open. Now I'm going to say a few things about surface facilities, but later in this presentation. For now, all I need to say is that intermittent lift creates upsets in the high pressure side of the system and also on the low pressure side of the system, and we better be prepared for that. Now, how do we do gas lift? Well, the first thing that we need to know is that there are three things that we need to control. One is the cycle time, and we need to be able to change the cycle time so that we reach by iteration, we find the optimum cycle time, which is the time that maximizes the daily liquid production. The other thing that we need to control is the volume of gas, the total volume of gas that we inject per cycle. And we do that by selecting the right calibration pressure and spread of the valve, of the operating gas lift valve. And we also need to pass that volume of gas at the exact rate so that we can minimize the liquid fallback losses, as I said. And we do that by selecting the largest possible port of the operating gas lift valve. Do we use 1.5 inch OD valve, or do we use 1 inch OD valve? We prefer 1.5 inch valve because they have 3 advantages. The number one is that they last longer. We're talking about here thousands of cycles in the life of this valve. It can be 40,000 cycles, and they need to operate without failure. And usually 1.5 inch valve lasts longer than 1 inch valve. The other 2 advantages are 1.5 inch valve has a wider range of area ratios. The minimum area ratio of a 1.5 inch valve is much smaller than the minimum area ratio of the 1 inch valve, and that's very important, because if we end up with a area ratio that is greater than we need, we end up over injecting the well, which is precisely what we are trying to avoid. The other advantage is that the 1.5 inch valve have larger ports, and as I have mentioned, it is very important to have large ports in order to have a very large gas flow rate through the valve. Do we use spring-loaded or nitrogen-charged valve? Well, we try not to use nitrogen-charged valve because of the high flow rate that passes through the valve once the valve opens. There is a cooling effect there that makes the closing pressure of the valve be below its theoretical value. But that's not the only problem. The problem is also that it's very hard to predict that closing pressure. So it's going to give you a larger than needed spread, which is very bad, because that will end up we will end up over injecting the gas, which is precisely the opposite of what we want to accomplish, but in a way that is hard to predict. Okay, now the spring-loaded valve, on the other hand, they also have a problem, but it's the opposite problem. The problem is that they tend to give an actual spread that is lower than the one that is the theoretical value, the one that we calculate, and that has to do with the dynamic effect of the dynamic behavior of the gas lift valve. So if it's not unusual that you get a 30 to 50% reduction of the spread of the valve, because the closing pressure of the valve tend to be higher than the theoretical closing pressure of the valve. So, but in that case, there are several things that you need to know. First of all, they're very consistent. Okay, that reduction that I talked about, 30%, 40% reduction in the spread, is easier to predict. Once you know how your valve will behave in a given field, then it should be easy to predict how it will behave and which value of the area ratio you need. Like, for example, if you do your calculation and your calculation gives you a certain area ratio, you know that you have to increase that area ratio, but maybe going to the next one available, and so on. Do we use single element valve, or do we use a pilot valve? Well, of course, we prefer pilot valve. Pilot valve, the upper section of the pilot valve, that's where we control the spread of the valve, okay? In a way that is independent of the main port. The lower section of the pilot valve, that's where the main port is located, and is always large, larger than any port that you will find in a single element valve of the same size. So the ability to control the area ratio of the valve independently of the port is very important, because when you use single element valve to do intermittent gas lift, you have to use a large port to achieve that gas injection flow rate that you need. Then if you select a large port, necessarily the spread of the valve is going to be very large. So you're going to spend a lot of gas per cycle, and at the same time, the velocity that will go through the valve is not going to be large enough to produce the liquid slug at the velocity that will minimize the liquid fallback losses. So you have two things going wrong: too much gas per cycle at a velocity that is not correct. Okay, in some situations, like let's say for example the inside diameter of the casing is very small. So yes, you're going to need a very large area ratio. You take a 1 inch, a single element valve, and that will give you the spread. But you have to make sure that the gas flow rate will be adequate to pass the volume and increase the liquid velocity to minimize the fallback losses. Now, there are two ways that we can control the cycle time, and in order to achieve the optimal cycle time. One is called choke control, and the other one is surface control, using surface controller. Now, what is choke control? In choke control, we let the pilot valve do all the work. We have a needle valve installed along the injection line in the surface, and through that valve, a low volume or low gas flow rate passes. The gas flow rate that we have at the surface is very low compared to the gas flow rate that passes through the pilot valve once the pilot valve opens. That means that when the gas lift valve opens, the pressure in the annulus is going to decrease until the pilot valve closes. The gas flow rate in the surface is always very low and is constant. Okay, so as soon as the pilot valve closes, the annular pressure begins to increase very slowly until we reach again the opening of the pilot valve. So basically, all the gas that we pass into the tube per cycle comes from the annulus, and that has a very good effect on the high pressure side of the system. We can have many wells intermittent at the same time, but because most of the gas comes from the annulus, then the injection pressure of the gas lift manifold will not decrease. Okay, so but at the same time, if we have a large number of wells, then if we don't need to install intermitters, that you have to spend money buying those controllers, and then you have to maintain the controllers, and they need maintenance. So, but surface controllers they have a huge advantage, and if the system is not that very big, and then you might be able to use surface controller, because with surface controller you control not only the cycle time, by keeping the controlling close, by lowering or increasing the time the software controller is closed. But also you can fine-tune the volume that you pass per cycle by keeping the controller open for as long as it is necessary. So by keeping the controller open, the pilot valve will remain open. Okay, so you can fine-tune that volume, the net volume per cycle, which is something that you cannot do with show control. With show control, once we install the valve, well, what will allow, the only thing that controls the volume of gas per cycle is the spread of the valve. So if we made a mistake with the spread of the valve, if it is too big or too small, then that's it. We will have to replace the valve. So there are in most of the time, I have found that if you do your calculation correctly, you should be able to do show control. Okay. Okay. Do we use plungers or not? Plungers are very difficult. I'm talking about here plunger assisted intermittent gas lift. With plunger, you have to have, it increases your maintenance costs and so on. But if the system is not able to provide the volume, the gas flow rate through the pilot valve to sustain a high liquid slug velocity, then you're gonna have a huge fallback losses. And the problem with the velocity of the liquid slug is that if it is very, very slow, if it moves very slowly, then the gas will tend to bubble through the slug. If it travels at a very high velocity, then the gas will tend to break through the slug. So there is an optimum velocity that you should be able to find that velocity. It is usually around 1,000 feet per minute, but it's easy to find the optimum velocity in the field. So yes, you might end up using plunger so that you keep the fallback losses at a minimum. In two cases, the one is when the liquid velocity is not very big because your system the injection pressure is not that high, or in cases where the point of injection depth is very, very big. I forgot to mention something about the pilot valve. Many people think that because if you install an intermitter, then you shouldn't be able, you can just get by with a single element valve. Some people have even told me that why not using intermitters and an orifice valve? Well, of course, orifice valve, what happens is when the intermitter closes, then all the volume in the annulus will go through the orifice, and then you're going to have to increase the pressure again inside the annulus by a lot. So no. The fact that the best combination that you can have, and probably the only one in many cases, is an intermitter and a pilot valve. Second stage optimization has to do with replacing the current completion with a different type of completion in order to increase the efficiency of the method. Now, the first thing that we need to do is to always check if we can prolong continuous gas lift while reducing the injection gas liquid ratio, because it is always better to produce the well on continuous gas lift than on intermittent lift. There are many operational reasons for that. Now, we can do that by reducing the tubing size or using velocity strings. That's the first check that we need to do. There are places where, for some reason, the packer cannot be installed as deep as possible, or maybe the perforated interval is very long, In those cases, it's a good idea to check if using, for example, the completion proposed by Schlumberger, which is called perf lift, or by Weatherford, which is called extra lift. And I'm trying to see if we can lower the point of injection. Now, if you're going to use this type of completion, do not use it for intermittent lift, because producing the well in intermittent lift through an annular space, and you're pushing the liquids from below, okay, the losses, the fallback losses are going to be huge. And but even if you're using this type of completion for continuous gas lift, you need to pay attention to instabilities caused by large flow area and or terrain-induced instability. We're going to be producing below the bubble point pressure, and the horizontal section of the well might be very long, so we might have terrain-induced instability. If we're going to extend gas lift all the way to ultimate depletion, then we really need to use other type of completion that are specifically designed for intermittent gas lift, and that's what I'm going to explain next. The first type of completion that I'm going to explain for intermittent gas lift is the chamber installation. More liquid can be accumulated for a given bottom hole flowing pressure using this type of completion. This is what we call double packer chamber. We have an upper packer here and a lower packer. The lower packer is located right above the top of the perforation, and the upper packer is at a distance that is determined by the optimal cycle time. We need to calculate the optimal cycle time, and from there we will calculate the distance between the two packers. The way it operates is as follows. At the beginning of the cycle, the valve, the operating valve, which should be here, is closed, and the entire chamber, which has an annulus volume and a deep tube, is filled with injection gas from the previous cycle. So the liquids are traveling from the reservoir, and they go into the deep tube through the standing valve located right here, and into the annulus through the perforated nipple, which is right above the lower packer. So the liquid level here will rise, and the gas that is trapped above it needs to be vented back into the tubing, and from there to the surface. And that's the reason we have to have here a bleed valve. Once the entire chamber is filled with liquid, then the operating valve will open, and gas is injected into the annulus through a snorkel that goes through the upper packer, and liquids are forced downwards and into the perforated nipple. This standing valve will close, and then you generate a liquid column that is the gas move from here all the way to the surface. Now, with this type of completion, we can always reduce the injection gas liquid ratio. We can always increase the liquid production, but it will be significant in those cases where the PI tends to be high. We should expect an increase in production from 60 to about 80% of what we have with a normal type of simple type of completion. Now, it is true that once all the liquids is generated here in the tubing, that the liquid slug will be about 300 or 400 greater or longer than the liquid slug that we will get in a simple type of completion. But that doesn't mean that you're going to increase the liquid production by that amount. The reason is that as much as it is true that you're going to generate very large liquid column per cycle, it is also true that you're going to have to wait more time in order to fill the entire volume of the chamber, and so you end up with less cycles per day. But at each cycle, you produce much more liquid, and that's where the injection of the reduction in the injection gas liquid ratio lies. Okay. Now we have to make sure that we pay attention to several things here. I've been in many places around the world, and they have told me that they don't want to do this type of completion because they tried that in the past and it just didn't work. Well, I did a complete troubleshoot analysis in Lake Maracaibo one time, and there were 10 wells there, and they were not producing any. The increase in production wasn't there. In fact, the injection gas liquid ratio went up. So what I did was using waterline operation. I placed a pressure and temperature sensor between the standing valve and the perforated nipple, and then I produced the well for several cycles. At the end of that, I closed the gas injection. I allowed the final cycle to reach the point where the liquid is filling the entire chamber, and then I did 2 additional stops, one in the middle and one at the top of the chamber. So that's from there you get all the information that you need in order to calculate the fallback losses, the PI of the well, and so on. And you should be able to do that analytically once you have all the information from the pressure source. And that's the reason I always recommend to have at least 2 joints between this standing valve and the perforated nipple. So one thing that I found in Lake Maracaibo was that the liquid column, or the liquid level in the annulus of the chamber was way below the liquid level in the deep tube. And the reason was that the port of the size of the port in the bleed valve was very small. So the gas was not vented properly. That's one of the things that we have to worry about with this type of completion. Now, also, if the gas-oil ratio is very high, you end up filling the whole thing with liquid that has very light gradient. That means that there is a lot of gas still in solution, and you end up filling the whole thing with the net volume here of the liquid is not as you expect. It's actually less, much less than that. If you produce sand, if the well is producing sand, then this type of completion is not recommended because it might be difficult to pull the completion or do performing waterline jobs. We do have a special designs for the standing valve, so that is it will clean every time you inject gas. Okay, get rid of the sand that accumulates here. And if the well produces a lot of gas, then we also have an arrangement here so that the liquid will have to go first. Will have to go up and then down and then into the perforated nipple so that arrangement will act as a separator, a gas separator there. There are a few things that we can do to take care of these 2 problems. Now, when you're doing the design, keep in mind that the operating valve, which is right here, is which should be a pilot valve. The temperature is equal to the temperature of the geothermal temperature, basically, because it is located way above the liquid accumulation point. The other thing is that many people make the mistake of when they're doing the spacing of the mandrels, they say, oh, okay, I reach here, I'm already here at the top of the valve, I can use this as the unloading valve and also as the operating valve. Okay, that's what we do when we're doing normal intermittent lift in a simple type of completion. But here you have something to worry about, that not only the pressure needs to be able to send the liquid from columns from the operating valve to this unloading valve to the surface, but also all the liquid that is accumulated here. If the pressure is high enough to do that, then yeah, fine, you can do that. This operating pressure can be one of the last unloading valve, this operating valve here. Now, if that's not the case, then you should have two mandrels here located at a distance apart from each other so that you can perform waterline operations, and use one as the unloading valve and the other one as the operating valve. Also, keep in mind that the reservoir pressure is going to decline. So if you calculate the length of the chamber based on current reservoir pressure, pretty soon you're going to find out that the optimal cycle time takes place when the chamber is not filling completely. Okay, so always multiply the length that you get from the optimal cycle time at current conditions by maybe 0.7 or 0.8. It depends on how you expect the reservoir pressure to decrease. Also, keep in mind that, that there are two things that you have to worry about generating this large liquid column. One is that if you make this the distance between the two packers, even after applying this reduction, 70% or 80%, the liquid column might be too big, and you should calculate how, and there are many ways of doing this. You should make sure that the instantaneous gas flow rate through this pilot valve is high enough so that the liquid, even though it's very large, it will reach a velocity in which you minimize the fallback losses. And the other thing is that because the liquid columns that you're going to generate are very large, the hydrostatic pressure might open one of the unloading valves as the liquid slug passes by each of them. And so if we have to avoid that, because that will be an inefficient operation. The other thing that you need to know is that this is a completion that is more complex, and you might have inefficiency caused by mechanical failures. Keep that in mind. This completion is what we call insert chamber. The chamber will be right here, and it can be located below or along the perforated interval. And with this type of arrangement, the inside of the chamber, it acts exactly like the double packer chamber, but now the combination of this bleed valve here that we need to have two bleed valves, one for the annulus of the chamber itself and the other for the gas coming from the reservoir. Okay, and but that combination acts as a separator, as a huge separator, because gas will try to go up and the liquids will go down. So you should be able to handle gas in a better way. Okay, but the operation of this type of completion is exactly the same. And yes, you can always reduce the injection gas liquid ratio. Now you will have an increase in production, and not necessarily in very high PIs. In fact, with this type of completion, you can really reach 200 or 300% increase in production. Of course, the chamber has to be below the top of the perforation, and this has to be a long perforated interval or maybe a long rat hole. Okay. Now, you should be able to drastically increase the liquid production, because this type of arrangement generates the maximum drawdown, and especially suitable for wells with long perforated intervals. Now, attention, you have to pay attention to the port size of this bleed valve and also on this bleed valve. So you now have two things to worry about. If you look at many old books in the production operation books, you will not find this. They just didn't exist, and we found out the hard way that you have to have this port. This is very, very important. Otherwise, you will have problems. I'm going to talk more about this because this is very tricky when I explain insert accumulators. For gassy well, it can handle gas, as I said, it can handle gas in a better way. Regarding sand, well, we shouldn't really try this completion if the well produces sand. And this completion is even more complex than the old package chamber, so that you can have inefficiency caused by mechanical failures. There are many other types of chamber, but I decided to stay with these two that I have explained so far because they are the most important ones. Now let's look at accumulators. They're very simple type of completion. Compared with simple completion, more liquid can be accumulated for a given bottom hole flowing pressure, but with less complex completions. This is what we call a simple type accumulator, and it's nothing more than having the inside diameter of the tubing, of the production tubing, slightly greater than the inside diameter of the rest of the production tubing, and right at the point where we're going to generate the liquid column. Now, this is not drawn to scale, of course. Usually, the length of the accumulator is much less than the TVD or measure depth of the entire tubing. Now, with this type of completion, we can reduce the injection gas liquid ratio. We might increase the liquid production, but the PI has to be high. Usually, we should expect from 10 to 15% increase in production. It's very, very suitable for gassy well, and it's not as complex. It's just a enhanced simple type of completion for intermittent gas lift. But we do have to pay attention to the liquid capacity, to the fact that the liquid capacity is always lower than any type of chamber, and also the inside diameter of the accumulator cannot be too large. And the reason for that is that first, if we make this diameter very big, then we're going to have to make sure that the instantaneous gas flow rate through the operating valve is high enough so that the slot velocity is high, so that we can reduce or minimize the fallback losses when the interface between the injection gas and the liquid slug is traveling along this the accumulator. And the other thing is the fact that we're going to generate a large liquid column here, and we need also to make sure that the pressure is high enough and the gas flow rate is high enough so that the liquid slug will travel at a high velocity. And for that reason, we in order to minimize the fallback losses in the accumulator, we usually recommend having a distance around 100 feet from the entrance of the accumulator to the point where the operating valve is located. In that way, when the injection gas enters the accumulator, the liquids have already a velocity, and that minimizes the fallback losses. This is what we call insert type accumulator. This will be this tubing right here, and the way it operates is as follows. At the beginning of the cycle, this is filled with gas from the previous injection gas from the previous cycle, and so here this arrangement will act as a huge separator, so that the gas will tend to go up and through this upper standing valve, and the liquids will go down and into the accumulator through this standing valve. So what's going to happen is that early in the cycle, while you're generating the liquid column here, the gradient here is going to be much greater than the gradient here. So early in the cycle, this standing valve will close, and we should be able to handle everything through this valve. This should not be designed only to handle or to vent the gas from the separator, and because we should take advantage of the fact that the liquids will travel here through this upper standing valve. So the liquid will go through here and into the tubing. The liquid will drop, and most of the liquid that accumulates here in the accumulator is coming from here, not from here. And the gas is handled very, very nicely because it will go up. Okay. So once this accumulator is filled with liquid, then the operating valve, which is located right here, will open, and the gas will be injected down this coil tubing or parallel tubing, small diameter tubing, and into the accumulator to push the liquid slug all the way up. Here we will have an LT type of mandrel. An LT type of mandrel is like the mandrels that we use for chemical injection, right? With this type of completion, we can always reduce the injection gas liquid ratio, and because of the very high drawdown, we will have an increase in liquid production. I have used this type of completion in several wells in Lake Maracaibo, and I have increased the liquid production by more than 400% in many cases. They are very suitable for gassy wells, and they are not as complex as insert chamber. But we do have to pay attention to several things. The first one is that we should always have the operating valve here and not in the LT mandrel. The reason for that is that if we put the operating valve here, then because of the pressure drop along this tubing, the valve will close at a pressure that is much lower than the pressure that you have in the annulus, so that the volume of gas that enters the tubing is only a fraction of what you will have if you have the valve here. If you put the gas lift valve here, then the pressure drop that you will see here, or the spread of the valve that you will see here, is the spread of the valve that you have installed at the operating point of injection. So you have more control on that. The other thing that of course, the inside diameter of the accumulator cannot be too large for the same reason that I explained for simple type accumulator. We don't want to have a huge fallback losses here because of the diameter being too large, and we don't want to generate very high liquid column that will be very hard to send to the surface, to push to the surface at a velocity that will minimize the fallback losses. Now, and of course, this here should not be designed for single phase gas flow, but for multi-phase and flow, and is extremely important. If you want to simply lower the point of injection for whatever reason, maybe the packer cannot be installed as deep as you should. This is the way that you should lower the point of injection when you're going to use intermittent gas lift. I have already shown the ideas from Weatherford, which is called extra lift, and from Schlumberger, which is called perf lift. They're fine. They're fine if you need to keep producing the well in continuous gas lift. But as I mentioned, those type of completions are not suitable for intermittent gas lift because of the increase in the fallback losses due to the fact that you're going to have to move the liquids up through an annular area, flow area. Okay. Now let me say a few things about automation, control, and data acquisition. Many people think that because the wells are now not going to produce as much as they used to, we shouldn't pay or we shouldn't invest money on this type of things. And actually it's quite the opposite, because now more than ever we should be able to control the optimal cycle time, and also we should be able to fine-tune the volume of gas that we inject per cycle. And for example, if we have a field where we have a reduced number of wells, and we have many intermediates working, and we might want to produce the well in a different way, just by implementing a type of control system that uses the pressure that we measure downstream of the intermediate as a parameter to control the opening of the intermediate itself. So for example, the intermediate might, instead of closing to 0% gas, it might close to probably allow a very low gas flow rate. And at that time, when the intermediate closes, almost close, then the annulus pressure should decrease, because the volume of the gas flow rate through the operating valve is very high now compared to what we are allowing to enter into the annulus. So eventually the pilot valve will close. But once the pilot valve closes, then the pressure in the annulus increases in the same way that it will increase in choke control intermittent lift. And eventually it will reach a pressure just below the opening pressure of the downhole valve. And at that moment, we close the intermediate 100%. And so that the pressure in the annulus will remain the same until we reach the optimal cycle time. And at that moment, the intermediate will open 100%. So that, but it will do so for only a short period of time, because the pressure in the annulus is almost equal to the opening pressure of the valve. So once the pressure increases to the opening pressure of the valve, then the intermediate can close. And in that way, most of the gas that is injected into the tubing is already in the annulus. So the high pressure side of the system doesn't see anything, and we can have wells that are intermittent on their own. We don't really care if too many intermediates are opening at the same time. Now, if you want a solution that is probably more practical, and this is something that has been tried for many years in Ventura field during the 90s, they introduced this type of control where you have a centralized control unit that will not allow many wells to intermit at the same time. And that's a huge advantage, and because it will not upset the high pressure side of the system, and at the same time it will not cause any problem also in the low pressure side of the system, like for example a separator. I'm going to say more about separators in the next slide. And now we have software, production system optimization software. We have a GAP that is capable of analyzing transient or non-steady state situations. And if we have the data and we want to explore the impact that a very strong well we're going to produce an intermittent gas lift, that the impact that this well will have in the high pressure side or the low pressure side of the system, we can do that now, but we have to have the data for that. And also now we have many things like artificial intelligence and data mining and all these algorithms that will help us optimize the field if the data is available and reliable. So the major drawback, you might say, well, is cost, but new technologies are reducing the cost. Now we can have Internet of Things located in different places in the field, and we can run optimization algorithm in the cloud and keep an eye on everything with a relatively small cost. Now let me say a few things about software facility. We need to adapt to a new reality, and maybe one of the ways that we can increase the production of the wells that are producing an intermittent and continuous gas lift is by lowering the wellhead pressure and the production wellhead pressure. But we have to know how to do it. Like for example, if we want to lower the wellhead pressure from 160 psi to 80 psi, then you need to know that the volume of gas, the actual volume or in situ volume of gas that is going to be handled by the separators is going to be increased by a factor of 2. Okay. Also, you're going to need a booster compressor to increase the pressure now to what the inlet pressure of the current compressor is. You might also have oversized test separators, because now the wells are producing, not only they are producing less volume per day, but also they're producing in batches. So you need to keep an eye, you have to adapt to that, and that means in many situations that you need to redesign the well you do well test. And there are many ways of low cost of increasing the accuracy of the well test. On the other hand, you might have undersized production separator, because they don't have the ability to handle many intermittent gas lift wells. So when that is a problem, a temporary solution might be to select some very strong wells that are causing the problem and install a choke along the flow line. But you have to do that away from the wellhead. You have to do that probably very close to the production manifold, so that when the liquid slug reaches the surface, it will encounter that choke when all the liquid is already in the surface. Yes, you're going to create a temporary increase of the pressure, of the back pressure of that particular well, but you're going to eliminate the problem at the separator, which might be a problem that will not allow you to produce the well at all. Okay. Now you need to know that you're going to have to handle gas with that in all pipes that and choke the pilot valve, the debris and solid particles with the gas might clog pilot valve. So you might have to install some kind of filter to so that the gas that is injected into the well is clean. You also have to somehow reduce all the restriction at the wellhead, in the flow line close to the wellhead or in the wellhead itself. Get rid of all unnecessary T's and elbows and valves, and get rid of also choke housings if it is creating a problem. Remember that a 20 barrels a day well that is producing, and every time the liquid slug reaches the surface at about 1,000 feet per minute, it's like having an 8,000 barrels per day well at that moment. So any restriction there at the wellhead is going to create a lot of liquid fallback losses. Liquid fallback losses take place usually at the very beginning of the cycle, of the injection cycle, because you are accelerating the liquid slug, but also at the wellhead if you find many restrictions there. In those cases where you still have a lot of continuous gas lift wells, you can use valves, calibrated valve or IPO valve instead of orifice. And at as the operating point to reduce the impact of compressor shutdown if they are frequent. Okay, in that way, if you have a shutdown, then the pressure in the annulus of those continuous gas lift valves will reduce just a little bit. The operating valve will close, and then the pressure in the annulus will remain high, and that way you save compression and gas. The other thing that you might do is to use abandoned wells and pipelines to store either high or low pressure gas to increase the stability of the whole system. The larger the volume of the gas in the high pressure side of the system, that is, all the pipes that go from the outlet of the compressor to the wellhead, if that volume is large, then the stability of the system is going to be, very stable. And the same applies for all the pipes that go from the separator to the inlet of the compressor. Well, finally, we can conclude that yes, the injection gas liquid ratio can be kept within an economical level if the proper steps are taken. Long-term planning for surface and subsurface equipment replacement can extend the gas lift method up to ultimate depletion. New technologies in automation equipment should make its implementation economically feasible, even and especially for low producing wells. And also keep in mind that training is one of the most important things. Throughout this presentation, I have mentioned that we need to calculate the liquid for bag, or we need to calculate the slug velocity, or the volume of gas that we inject per cycle, the optimal cycle time, the time that the intermitter has to remain open or closed, and so on. That requires having the proper tools that you don't find in commercially available software. And also the engineer has to be exposed to the new type of technicalities that are associated with the intermittent gas lift method, like all the type of gas lift valve, pilot valves that are there out there commercially available, and different types of intermitters, plungers, and so on. So training is one of the things that I would say that is the most important thing if you really want to extend the efficiency or keep a very high efficiency of wells in a situation where the reservoir pressure is going down. Thank you very much. This concludes my presentation, so if you have any questions, I will be very happy to answer them.